Hello everyone, this is Daniel from the Learning Center, and today we will be covering how to calculate pH during a weak acid strong base titration. That is, when a weak acid is being titrated by a strong base. We will be calculating the pH for 3 different regions. That is, one at the beginning when no base has been added, here as you can see with the yellow dot. We're going to be calculating it again at the equivalence point, which is about here where the green dot is. And then we'll also be calculating the pH somewhere before equivalence point in this red box, as well as sometime after equivalence, which is in this blue box. So part A refers to the yellow dot, part B refers to the red box, and part C refers to the green dot, and part D refers to the blue box. Well, let's take a look at this problem. A 25 milliliter sample of 0.1 molarity propanoic acid, which is given here as HC3H5O2 with a Ka of 1.3 times 10 to the negative fifth, is titrated with a base 0.1 molarity sodium hydroxide solution. And for each part, we have A, calculate the pH when no base has been added yet, which is on this graph is right here at the yellow dot. And then part B, calculate the pH after 515 milliliters have been added, which is in this red box. And then pH at the equivalence point, which is at this green dot, and then pH after 26 milliliters of base has been added, which is at this blue box. So let's go ahead and start with part A, which is pH after no base has been added. Let's first start off by writing down the information that we already have. We have our acid, which is C3H5O2. C5O2, H5O2, with a Ka of 1.3 times 10 to the negative fifth. We know that our acid has 0.1 molarity, starting off with 0.25 liters of solution. And then our base is also 0.1 molarity. So first, let's start off by writing the equation, or writing the reaction for the acid before we add any base. So we have HA, which is our propanoic acid. I'm just using a shorthand so I don't have to write it out each time. And this will dissociate in water into H+ ions and some of its conjugate. All of this occurring with a Ka of 1.3 times 10 to the negative fifth. So we're going to use a tool called an ice chart, which stands for initial, change, and equilibrium. And remember, an ice chart has to use molarity values. So what is the initial molarity for our acid, HA? That will be given right here. So it is 0.1 molarity. And what is our initial molarity for acid and for the protons and its conjugate? The protons and the conjugate, it will be 0, because the reaction has not occurred initially. At the beginning of the reaction, nothing has been converted yet. Now, what's the change that's going to happen? Well, the reaction is going to shift towards the right, meaning that less acid, and we'll be making more protons and conjugate. So plus X and plus X for over here. And for equilibrium, we'll have 0.1 molarity minus X, and H plus will be just X, and the conjugate will also be just X. So we need to find pH. The goal is pH. What is our pH? Well, pH is just a way to denote H plus concentration. So we need to be solving for this X value. To do that, we have to use the Ka. The Ka will be equal to the concentration of the products over the concentration of the reactants. So this will be H plus concentration times A minus concentration over acid concentration. And if we start plugging in these values, we will get X. I don't want to use blue, I want to use X times X over 0.1 molarity minus X. I'm starting to run out of space here. Let's like scoot over a little bit. There you go. Now, this is really difficult to solve. 1.3 times 10 to the negative fifth is equal to X squared over 0.1 molarity minus X. This is a bit tough to solve. Luckily, we can use the approximation. That is being said that if X is small enough, if X is small enough, 0 minus X will also just somewhat be just 0.1. We know if X is small enough if the Ka is small enough, and this Ka happens to be small enough so that we can use the approximation. So we can get rid of this. And that means we can just get rid of this minus X in the bottom. And our final equation becomes X squared over 0.1. Solving for X, we get that X is equal to 1.4 times 10 to the negative third molarity. Now, it looks like we're done, except remember, we're solving for pH right here, pH. And X, as you can see here, is only H plus concentration. So how do we get pH from H plus concentration? pH is equal to negative log of H plus concentration. Plugging in our previous value, we get negative log of 1.14 e to the negative 3 molarity. Plugging that into your calculator, you'll get that pH is equal to 2.94. And bam, there's our answer for part A. Okay, moving on to part 2. Part 2. What is the pH after 15 ml of base is added? Now, this one will be a little bit difficult. Remember, we are solving for this region now, which is before equivalence point. To do that, we'll have to use something called a mole chart. Mole chart, which sneakily will look like an ice chart, except remember an ice chart must use molarity values, and this mole chart will be working in moles, not molarity. So a good place to start again is to write our equation. It says that what is the pH after 15 mL of base is added? So we have our acid, we're going to add some base, which is OH minus, and the reaction is going to proceed forward and create water and conjugate base. Remember, this is a mole chart, even though it looks like an ice chart. we need to calculate HA, or our acid amount in moles. To do that, remember that molarity is equal to moles over volume in liters. Rearranging that, mole of HA is equal to 0.1 molarity times our volume of 0.025 liters, and we get 0.0025 mole. We have to do the same for the base, OH minus. Luckily, pretty similar. The base also has 0.1 molarity. Multiply that by 0.015 liters, and we get 0.0015 mole. Let's plug those values in right here. So we have 0.0025, 0.015, and our initials for water and the conjugate are 0. The change, we know what the change will be. Whichever one of these is smaller, you'll be subtracting from the other, or from everything actually, on the left side. So since OH is smaller, we're getting rid of all this OH because it's reacting with all of this acid, and it's being converted to water. I messed up there. And it's being converted into water, so we add it to the other side. And we get 0.001. We have 0 here for the base, and 0.0015 for water, which is not important, and 0.015 for the conjugate, which is important. Notice this. We have both the acid and its conjugate in solution at the exact same time. When you see that, you have to be thinking buffer. And because this happens to be a buffer solution, we get to use a special equation, which I'm sure you guys have covered, the Henderson-Hasselbalch equation. Henderson-Hasselbalch. I may have misspelled it, but it is pH is equal to pKa plus log of the base over the acid. Plugging in our values, pH is equal to pKa, which is the negative log of our Ka. Ka is 1.3 times 10 to the negative 5th, plus the log of the concentration, or the amount of base in our solution, which is right here. And so that is 0.0015. And the amount of our acid, which is right here, so over 1.110. That fulfills the equation, and if we plug that into our calculator, we will get that pH is equal to 5.06, which makes sense. Before we add any base, our pH is just 2.94, so we're getting a little bit more basic as we're adding more base. We're getting there, so this is our answer. This makes sense. Okay. Let's see, moving on to part C. Part C says the pH at the equivalence point. Now the equivalence point is when the moles of acid is equal to the moles of base. At this point, you have completely neutralized all the weak acid with your base. So let's do the same thing as part B, which is creating a mole chart. We happen to use the same reaction, which is HA plus OH minus yields H2O plus A minus. Now part C is definitely the trickiest of all these problems. We have initial and change. Our initial is the same as before. It is 0.0025 for the acid, and at equivalence point we know that the base has to match it, so it also has to be 0.25 moles. Of course, water and the conjugate are 0 because nothing has reacted yet. Now we react. Remember, you choose which one is smaller and subtract it from the reactants. They have to be both the same, so you just subtract 0.025, 0.025, and then you add that to the products, since we're using up all those reactants to make these products. In the end, we get no acid left, no base left. We have a plus of 0.0025 mole of water and 0.0025 mole of acid. Now, this is where it gets tricky. You might be wondering, how do we calculate the pH from this? We can't use Henderson-Hasselbalch. I don't see any H pluses anywhere. Well, what we can do is we see that there's this OH here, and we see that everything has been converted into a conjugate. The conjugate itself also has a KEQ value. So our Ka is 1.3 times 10 to the negative fifth, but the Kb, which is the opposite reaction, the reaction that goes that way to the left, our Kb also exists, and we have to flip the reaction to solve for it. So our new reaction is A minus plus H2O in equilibrium yields HA plus OH minus. And for this, we'll have to use an ice chart because we are in equilibrium. Because we're in equilibrium, we have to use an ice chart. Ice chart means we have to use molarity values. First, let's calculate our Kb. Kb, so the relationship between Ka and Kb is that there is a Kw, which is equal to Ka times Kb. Rearranging this equation, we get Kb is equal to Kw over Ka. Kw is 1 times 10 to the negative 14th, and our Ka is 1.3 times 10 to the negative 5th. Plugging this into our calculator, we get that Kb is equal to 7.69. Write that out better. 7.69 times 10 to the negative 10th. Excellent. Now we have to calculate the concentration of our conjugate. We do have this value right here to use, but that's in moles. So how do we get moles into molarity? We have to use moles. How do we get moles into molarity? We have to use molarity is equal to moles times liters. This is where you need to remember that we've added volume to the solution. We've added volume in that we started off with this much acid, and then we slowly dripped more and more base, thus increasing the volume even more. So, what we need to do is first calculate the volume added, volume of base added, volume of base, and then we have to add it to our initial volume, V volume initial, to get our total volume. We can then use our total volume to calculate the molarity of the conjugate. So, how do we calculate volume? Once again, this equation is key. So, to calculate volume, we have volume is equal to mole over molarity, in this case 0.0025 mole over molarity of 0.1 molarity, and this yields 0.025 liters of base. This is base. So plugging that into here, we have 0.025 liter plus volume initial. Volume initial is also 0.025 liters, as given by right here in the equation, in the problem. So that means our total volume is 0.05 liter. Okay, I have to zoom out. I'm starting to run out of space. Now to calculate end molarity, let's call this molarity final, I guess. We have the same mole amount, which is 0.0025 mole, but now we plug in this volume amount, so 0.05 liter, and if we plug that into our calculator, we get a molarity of 0.5 molarity. Nice. So we save that answer. We gotta put that answer over here at 0.05 molarity. We don't care about water because it's a pure substance. It is not accounted for in the KB. And of course our HA and OH minus are 0. The change, we get rid of the conjugate base and we get more acid and more OH. This is starting to look a little bit familiar, I hope. OH is X, HA is X, and then conjugate base is 0.5 minus X. We have our KB value right over here. KB will equal the concentration of HA times the concentration of OH minus over the concentration of the conjugate A minus, which is 0, which is X squared over 0.05 minus X. We can still use the approximation since our KB value is small enough. So just get rid of that X and plug in 7.69 times 10 to the negative 10th is equal to X squared over 0.05. I'm just going to draw a line here to separate our calculations. We get X is equal to, let's see, if you plug that into your calculator, you will get X is equal to 6.20 times 10 to the negative 6 molarity. X here is X here, which as you can see is actually the OH concentration. We need to get pH. So we use the relationship POH plus pH is equal to 14. Solving for POH is equal to negative log of OH concentration. And we get negative log of 6.2 times 10 to the negative 6, which is 5.21. Almost done. pH is equal to 14 minus POH, which is equal to 14 minus 5.21, which gets our pH of 8.79. We're definitely getting more and more basic. Good. This answer looks right. And lastly, part D. Part D is we're calculating the pH after 0.26 mils have been added. Okay, same thing, add a mole chart. And we use the same reaction, HA plus OH minus yields water plus A minus. HA initial is 0.0025. OH minus, it says we've added 26 mils of base. To calculate that, remember, molarity is equal to moles over liters. Mole of OH will be 0.1 molarity times 0.026 liters, and we just get 0.0026 mole. So plug that in here, 0.0026. Of course, 0 for our initial amount of water and 0 for initial amount of conjugate base. Which one is smaller? This HA value, so subtract 0.25 from the reactants while adding it to the products. And we get nothing, we run out of acid, and we have an excess of base, and we create some water, which is not very important, and we create some conjugate base. Now the important thing to notice here is that we've left with a surplus of base, of OH, of hydroxide. So this calculation is pretty easy. We calculate the pOH from the negative log of OH concentration. We have to calculate that. Remember, molarity of OH should be 0.0001 mole, but the volume will be the total volume of the base added and plus the initial volume. So 0.025 liters for the initial and 0.026 for the base added. And we get a molarity of, let's see, .002 molarity. Plug that into our pOH equation. It's equal to negative log of 0.002, and we get our answer on pOH 1.71. And remember, pH is what we want. pH is equal to 14 minus pOH, which is equal to 14 minus 2.71. And that happens to be 11.29. And there's our final answer. And we have calculated the 4 main stages of a titration. So this is a very, very standard problem that you'll see in likely Chem 1B. And it's something that you'll often see on your exam, and this is just the basic format. This definitely won't help you get you through an exam, but it's definitely a good guide of calculating certain parts of a weak acid, strong base titration. Yeah, and that'll be all. Good luck on all your chemistry endeavors.